All right, so we'll recap of where we are. We talked about supervised learning, talked about deriving rules and arranging them into trees. We talked about how those trees are susceptible to overfitting. And we talked about one way of combating overfitting is to use ensembles of weak learners and combine their results to form a strong learner, and gave one example of this in random forest. We also mentioned that one disadvantage of these ensembles is they become pretty difficult to interpret, right? Because it's a big vote among a bunch of smaller models, and so it's not quite clear where the decisions are coming from. And random forest had one way of attacking this, in that as you build a random forest, it was producing an importance measure for the variables, right? So if particular attributes were more influential in the decision, you would get a measure of this as one of the outputs. And then we talked about k-nearest neighbors, which was a change in that it used numeric attributes. And continuing that, we're going to talk about gradient descent and some applications of it. Okay, so this, remember the three components of a machine learning solution is the representation of the model, the evaluation of that model, how you tell how well it's doing, and then how you optimize the process. And so the gradient descent is an optimization method that's applicable in a lot of different contexts that we'll touch on at the end. Okay, so in a nutshell, what you're doing here is expressing your learning problem in terms of some kind of a cost function that you want minimized. And starting at some initial point, you're going to roll the ball downhill until it settles in a trough. And so this process describes how to walk downhill. It's not really a roll, right? You're going to take steps, and that turns out to be one of the difficulties with gradient descent. Okay. And so some situations you can sort of design offer a guarantee that the minimum you find will be the global minimum, other times you don't. And so getting trapped in local minima for more complex problems that we won't go into too much detail on is another potential weakness of this method. Okay, so the problem we're going to be thinking about here is no longer classification, although we'll mention how you can use this for classification at the end. But we're going to think about just regression. Okay, and so regression can still be used as a prediction task, and we think about sort of fitting a line to data, but the point is you might use that line in order to make predictions of the outcome value, of the response variable given the inputs down the road. Okay, so a regression line is a predictor. Okay, so rather than a discrete class variable, we're maybe talking about a response variable that's continuous. Fine. So in this case, we'll take the very simple case of just a single input variable, but in throughout this, we're going to be thinking about an entire vector of input variables, and that vector you can think of it as a row in a database. Okay. All right. So imagine we have these points scattered this way, and you can see that this is a pretty cleanly produced data set where there is kind of a regression line that exists that probably describes the data pretty well. And in fact, that's not a surprise because I sort of generated to have that effect for illustrative purposes. So the process here is we're going to imagine that there is that we split the data first into a training set and a test set, and that's always the first thing you want to do if it hasn't been done for you already. And here we just split them half and half. And we talked to a couple of segments ago about various ways to do this, but here we're just going to train on one half and test on the other. And further, I've scaled the data so that the original domain here of -10 to 60, or really 0 to 60, and some kind of range of 0 to 600 is scaled down to variation around 0. This is actually a little suspect what I did here, because I scaled the data all at once and then split it into training and test data. And so the test data sort of influenced how the training data was scaled, which is typically a no-no. Okay, so you may want to scale them sort of separately. Right, so how does this gradient descent work? In this plot, what we have is the two parameters for the regression line, which are theta 0 and theta 1, and it's the y-intercept and the slope, essentially, right? These are the two parameters for a single line. This is the equation down here. I refers to the iteration number. Okay, so this is really iteration 0 that we're looking at, or really the difference between iteration 0 and 1. So we started this process off at this point, and we picked that point randomly, right? And there's various deterministic ways to choose a starting point, but in general, the fact that you have to decide a starting point is one of the weaknesses of gradient descent. Okay, so we start off at a single point, and then we found the direction of steepest descent and took a step in that direction. So the cost function here that we're trying to minimize, this says that the response variable y minus the function applied to the input variable, and here the function is just a linear regression of intercept plus slope. Take that difference and square it and add them all up for all the data points. Right? That's the total amount of error that you received by trying to explain all the data with this particular regression line that we started with, this first starting point. And so we compute that gradient, and I haven't shown on this slide how to do that, but you complete that gradient and jump down quite a bit, right? The error goes down a lot in this first step as we walk from here to here in this parameter space. So now we've gone from one regression line to another regression line. Here's the first regression line that we started with, and we just kind of got lucky that it already is kind of in the right direction. We may not have. It could have gone this way. All right. So the next slide, we take another step, and the error goes down a little bit more, and we take another step towards the minimum over here, toward the center, and we've got another regression line that has rotated slightly, so it's closer to what we intuitively think will be describing the data. And we can keep going with this and keep stepping down, and the regression line gets better and better and better. The error goes down, right? We're finding a local minimum in that error until we decide that it converges. When the difference between the error in iteration I and the error in iteration I plus 1 is less than some threshold, okay, then we decide that it's converged. And in fact, in this case, it looks like it did pretty well in that it got what we see as sort of the minimum here. And this line looks like it describes the data pretty well, which we can see on the next slide. So again, each one of these lines, this line is perhaps the slope and intercept, right? These two parameters, theta 1 is theta 0 and theta 1 from iteration 1, while this next line is the theta 0 and theta 1 from iteration 2. Okay. So at each step, we form a new line, test how well it describes the data, and proceed. But what I haven't said is how we figure out what direction to actually walk in, nor how far to walk. All right, so let's think about that.